Hi, my name is Rick Allen. I'm a professor of water resources engineering with the University of Idaho. I would like to talk today about reference evapotranspiration and a little bit about the history of some of the standardization efforts, some of the usages of reference ET, and also how it might be helpful in comparing against some of the crop water models that also produce evapotranspiration estimates. Uh, Most of the viewers are probably well aware of reference ET, but for those who are not, uh, reference ET is the evapotranspiration that is estimated to occur from some kind of surface of dense vegetation. And currently we have two definitions. One is for the clipped grass type of surface that usage is common around the world. And then a second one is alfalfa that we'll look at shortly. The primary purpose of reference ET is to help us to estimate the expected amount of ET from vegetation under well-watered conditions, a full leaf surface, and it represents essentially an upper limit on ET. And it's, of course, impacted primarily by weather. Weather is what, and the environment is what provides the energy to transform liquid water into vapor. The purpose of reference ET was just to help simplify the ET estimation process for the hundreds of crops that we have. If there were no reference ET, we would need to have a ET equation that was customized for every crop, for every stage of growth. And many users would, I'm sure, feel a lot of frustration if they had to go through parameterizations for every crop and every stage of growth. As I mentioned, there are two types of references used in the United States. Grass is very universal across the country, and it's a clipped grass. We'll talk about some of its characteristics in a minute. Alfalfa has a fair history dating back to the 1960s, and alfalfa reference is used primarily in the upper Midwest states and western northern states, for example, Idaho. The clipped grass is generally defined as either a fescue or perennial ryegrass, fairly robust cool season grass, mowed and maintained between about 8 and 15 centimeters in height. The FAO has further standardized that for the virtual clipped grass reference to be 12 centimeters in height. In contrast, alfalfa is a taller, leafier type of vegetation. There's a photo here in the lower right. And it's defined as an alfalfa crop being somewhere between 30 and 70 centimeters in height. 70 is pretty much the maximum height that most alfalfa varieties attain. And once we grow beyond 30 centimeters, generally we have sufficient leaf area of about 3 or so to essentially convert environmental energy into a maximum ET rate. And then we always, for a reference crop, we presume that it's in a fairly well-watered agricultural setting with no obstructions. You know, if we were to measure it, or if we are wanting to understand what it represents. So if you can envision the reference crop as being in an extensive field situation with no obstructions, and it has enough extent that the boundary layer that's built up over that crop, over that surface, is in equilibrium and synchronized with the surface, so that if we take air temperature, vapor pressure, wind speed at a few meters above the surface, those are representing what's going on at the surface as far as energy conversion and cooling and humidifying. So as we talked about, alfalfa is rougher and leafier than grass. And so alfalfa in general tends to evaporate, transpire about 20 to 40% higher than grass reference, depending upon how much dryness there is in the air and windiness. The windier it is, the drier the air, the larger the difference we see between alfalfa and grass, simply because alfalfa has more leaf area, and it's pretty much maximizing the conversion of energy from the environment, which includes solar radiation, long wave radiation from the atmosphere, and then any entrainment of sensible heat or thermal heat energy from the air down to the surface. And all of those combined represent an upper limit of the amount of energy that can be used to convert liquid to vapor. So if we have a definition like alfalfa reference, that pretty much represents the maximum extent of ET that we can envision, or that we can see occur. Plants cannot just magically push vapor into the atmosphere. It has to be pulled, and there has to be some mechanism inside the leaf to convert the liquid that comes up through the stem into a vapor, and that takes a substantial amount of energy. And so that's why we use the energy approach to estimate ET via the reference ET definition. That tells us what that upper limit might be. Currently, most communities around the world have adopted the Penman-Monteith equation shown here in the bottom. Penman-Monteith was developed in 1965 by John Monteith, where he took the Penman equation shown in the upper part here and brought in parameters that can better characterize the impacts of aerodynamic resistance, of how vapor can be transported from the leaf surface up into the boundary layer, and then also how any heat energy might be transferred from the boundary layer back down to the leaf or vice versa. Also, he put in the surface resistance term that tells the equation how difficult it is for water vapor to move from inside a leaf to the outside to be transported. And this is now a more physically based equation, and is quite accurate. The four parameters that the Penman-Monteith requires: it needs an estimate of net radiation, which is generally calculated using measured solar radiation. It would like to have an idea of the soil heat flux. In other words, how much of that energy that strikes the surface is conducted into the ground rather than being used to evaporate water. Fortunately, for a reference crop that has pretty dense coverage of the surface, G is usually only 5 to 10% of the net radiation. Then the other weather parameter we require in the Penman-Monteith is air temperature, and it's used in 4 or 5 different places in the equation to calculate saturation vapor pressure, calculate air density, to calculate the slope of the saturation vapor pressure curve. And then lastly, some type of vapor pressure or humidity term. Here we're looking at an actual vapor pressure expression as used in the Penman-Monteith. So this tells us something about the dryness of the air, especially when we look at the difference between the saturation vapor pressure and the actual vapor pressure, which is called the vapor pressure deficit. The larger this is, the thirstier the air is, and then coupled with wind speed, that estimates the value of the aerodynamic resistance. That tells us just how much drying power the air has above the surface. A few benchmarks in reference ET, as we talked about in 65, Monteith added the resistance terms to the Pimmin equation. That was actually in parallel with Reitema of Holland, who also in 65 in a Ph.D. dissertation brought in the resistances. So those two activities happened in parallel. In the 1960s, Bill Pruitt of the University of California, Davis led a lot of the effort for people to begin to adopt using the Pimmin equation. And then later in the 70s, the Pimmin-Monteith as an alternative to the more empirical equations like the Blaney-Criddle method. In 74, Marvin Jensen put out the first ASCE report on consumptive use that had substantial coverage and encouragement for usage of the Pimmin equation. And then that was followed in 1990 by ASCE Manual 70 that was encouraging, began to encourage the use of Pimmin-Monteith equation and standardization of it. And then that publication has been revised in 2016 to also encourage and recommend the use of the Pimmin-Monteith as a standardized reference method. Some of the reasons for standardization is if we go back into the 1970s, this is just a map that shows just a few of many wind functions that had been derived for the Pimmin equation by local research groups. Pruitt in California, Jim Wright, Marvin Jensen in Idaho, Gordon Cruz in Colorado, Dennis Kincaid in Colorado, Ken Hubbard in Nebraska, Tanner in Wisconsin, Kohler with the Weather Service, and Ted Samus down in New Mexico. They all had wind functions that were all different, and much of that difference in the wind function was probably caused by bias in the measurements of the reference ET that they were calibrating against, or it might have been due to bias in anemometers, humidity sensors, which back in the 60s, 70s were not nearly as accurate and dependable as they currently are. So much of the differences in wind function were probably not physically based or required. And so that's why beginning in the 1980s, ASCE and other groups worked to consider whether or not we could find a single equation that was physically enough based that it should be applicable in a wide variety of locations and conditions. And so that's why the Pimmin-Monteith was adapted. It's a very physically based equation given the availability of only the four weather parameter types: solar radiation, temperature, wind speed, and humidity. So the top equation we're seeing here is the full Pimmin-Monteith with the resistances. And then as part of the standardization work by FAO and ASCE, where the Pimmin-Monteith in the full form can be applied to any crop condition, you know, very small plants with 10% of the ground covered, all the way up through trees, depending on how the surface resistance and aerodynamic resistances are set. But for application as a reference, it becomes much more simple, especially when that reference has a constant height, constant leaf area. We can take our resistance formulations and set them more to constant values. And the result then is this bottom equation, which we refer to as the standardized Pimmin-Monteith, where we still have the same weather parameters, but now our resistances have been transformed to two coefficients, a numerator coefficient and a denominator coefficient. And then some of our terms like wind speed and temperature are more explicit in the standardized equation. A little more on history. Standardization was initially promoted amongst other groups by ASCE through Manual 70 in 1990. It was adopted by FAO in the 90s and brought into the FAO 56 publication in 1998. Then in 2005, a task committee of ASCE published a guideline shown here in the bottom right that provided step-by-step guidance on how to calculate the various parameters in the standardized Pima-Monteith equation, both for grass and for alfalfa. That's been fairly widely appreciated and accepted, that membership from all over the United States could come into agreement on some of the best practices for calculating reference ET. A little bit about these coefficients. The standardized ASCE Pima-Monteith can be applied to both alfalfa and grass references using the same equation. It can also be applied to both hourly and 24-hour or daily time steps just by selecting a different set of coefficients. So this table shows for the short reference, which is grass, and the tall reference, which is alfalfa. If one is calculating on a daily time step basis with daily time step weather data, here are the factors or coefficients for the short reference and tall reference. And then if one is calculating with hourly or shorter time period data, one uses a different set of coefficients. And then at nighttime, when there's less stomatal conductance, one can shift the denominator coefficient. So for the fixed settings in the standardization, we've had to just select one height rather than a range of heights. So for alfalfa, the community selected 1/2 meter height, which essentially reflects a leaf area index of about 4.5, surface resistance of about 30 seconds per meter. For the grass reference, that's been fixed at 12 centimeters in height, with that reflects a leaf area index of about 3 and a surface resistance of about 50 seconds per meter. So the clip grass does have a higher stomatal or surface resistance than the alfalfa, primarily because it has fewer leaf area. So that is one reason why, coupled with the taller height of the alfalfa, why maximum ET is generally greater from the alfalfa reference than from the grass by about 20 to 40%, depending upon the dryness of the local weather. A little bit about some comparisons between the Pima-Monteith and measurements. This is just showing a lysimeter system at Kimberly, Idaho, installed by the USDA clear back in 1965, 64. It's a big tank that's put on a large truck scale balanced electronic, and it weighs this tank full of soil and water and vegetation, and as water evaporates out, this tank weighs less, and we look at the difference in weight over time, and that tells us what the evapotranspiration would be. Here's the lysimeter field. The lysimeter is located about here, so we had good fetch, that 50 meters or preferably even greater that we talked about was there. And a good lysimeter is one where you cannot see it. The vegetation inside is identical to that outside. It matches outside to inside, and so we get a very good sample of a field scale evapotranspiration estimate. I want to show you just a couple time series here. This is hourly measurements by the lysimeter for 2 days, just showing through the course of the day. The dark blue is the calculated value, and the purple is the lysimeter measured value from that same lysimeter we just looked at by Dr. Jim Wright who was with the ARS in Kimberly for a number of years. And here's a nice clear day without any clouds, and we can see that the ET follows solar radiation quite closely. And we can see that the Pema-Monteith equation mimics the measurements quite well, even at night, which is fairly impressive. The zero line is right here. So we are seeing some positive evapotranspiration at night, although it's much less, of course, than during the day. And then a couple of days later, we have a similar, probably cloud-free situation in the morning, but in the afternoon, a large weather system came through with a lot of cloudiness, and evapotranspiration responded to that reduction in available energy, much less solar radiation, probably colder conditions. And we see that the Pema-Monteith equation reacted very similarly based on the weather data that were measured, as did the lysimeter that was just reacting to how much liquid water was being transformed into vapor. So these types of graphs give us a lot of confidence that the Pema-Monteith equation used as a reference to represent a full cover vegetation has pretty much all of the parameters required to follow what occurs in nature. Here's another look at some of the data from Kimberly. In this case, it's 24-hour measurements. The dark blue is the lysimeter, the light blue is the ASE Pema-Monteith, and this is over one growing season in 1969 at Kimberly. These whited out periods are periods where the lysimeter crop was harvested and then regrew over about a 15-20 day period. And of course, when it's regrowing, it's shorter than the 30 to 70 centimeter range that we require to represent enough foliage and vegetation leaf area to reach close to maximum ET. So those periods, we shouldn't expect the full cover equation to agree with the lysimeter that is growing a smaller amount of vegetation. But in all, we can see as the weather varies, measurements went up, the equation went up, and it's not perfectly following the measurements, but generally it's quite close. Early spring through midsummer into the fall, so under a fairly wide range of conditions. Here are those same data, but for a 3-year period where the lysimeter was measuring alfalfa. So here's the ASE Pema-Monteith estimates for the alfalfa reference versus the lysimeter. And we can see a pretty good one-to-one correspondence, a slope of 1 and an R-squared of about 0.7. Standard error of estimate of about 1 millimeter per day, which is fairly characteristic as we move around the United States. Well, what's the impact of time steps? Should we use hourly or daily? Here's some calculations of grass reference evapotranspiration using both a daily and an hourly time step with some data from the CIMMYS station near Davis, California. And fortunately, using those standardized coefficients, we can come up with very similar estimates of 24-hour evapotranspiration, whether we use 24-hour weather data or if we calculate with hourly data and then sum over the 24-hour period. So that's a nice outcome. So it shows some of the flexibility of the Pema-Monteith method. For alfalfa, there's a little bit more difference, about 3% between a 24-hour calculation time step and hourly calculation time step, but this is probably within the, say, 5% uncertainty of the equation itself. Again, this was calculated with data from the CIMMYS station, but for the alfalfa reference. So I'd like to talk a little bit about how we can use reference ET to represent a near maximum of ET. We've talked about already that transformation of liquid water to vapor requires substantial amounts of energy. That energy has to either come from solar radiation or thermal radiation radiated from the atmosphere, or some transport, we can call it advection of thermal energy from the overlying airstream down to the surface. Or perhaps a little bit of energy coming out of the ground, conducted out of the ground. But that's the only source of energy we have. We have to have it to evaporate liquid water. It's just like putting a pot of water on our stove or cooktop. That water will not evaporate until we add energy. It's the same story with evapotranspiration. So that's to our advantage, because if we can do a good job of estimating all of the environmental parameters, air temperature, solar radiation, wind speed, and humidity, Pima-Monteith with the reference gives us a very good estimation of what the maximum evapotranspiration rate might be. One indication that, in this case, the alfalfa reference ET represents a near maximum ET rate is that a number of crop coefficients developed, in this case by Jim Wright at Kimberly, for about 8 different crops common to southern Idaho. The crop coefficient, which is defined as the ratio of actual ET to the reference, reaches a maximum value of about 1 during the mid part of the growing season when that crop is at near full ground cover. What that tells us is that many crops that have extensive leaf area and whatever height they reach, anywhere from 0.5 meter to a couple meters for maize, approach the same upper limit on ET as the alfalfa reference. And that makes good sense because they are all consuming pretty much the maximum amount of environmental energy that's available. So that's an advantage to us, the fact that we can expect any crop to reach a KC of about 1.0 if we are using the alfalfa reference. If we're using a clipped grass reference, we might see the KC reach 1.2 to 1.4 simply because many agricultural crops have more leaf area than grass, or taller, so there's more mixing than the grass reference. The only
okay, I found this on the web for 21.4 simply because
excuse me, the only crop that had a KC less than 1 was potatoes, just because there was more stomatal control with the russet potatoes that Jim Wright grew as compared to the alfalfa reference. Another opportunity to see this maximum conversion of energy is to look at some of the products from remote sensing of ET, in this case with the metric model that uses Landsat thermal data to apply a full surface energy balance on a 30 meter by 30 meter pixel basis for a wide area, so we can actually observe hundreds of crops or hundreds of fields at any one time. And when we get to the center of the growing season, for example, with these sugar beets, what we see is that nearly every field, and in southern Idaho, fields are pretty well managed and watered, so they're all approaching well-watered ET. We see that nearly every field has a similar evapotranspiration value. In this case, again, we're expressing it as the crop coefficient. So actual ET from the field divided by, in this case, an alfalfa reference ET. And so a value of 1 means that these sugar beet fields and crops are evaporating and transpiring very similar to the alfalfa reference amount, which makes good sense. So each of these little points is 1 field, and then the large black symbols are the average overall fields, and we can see the characteristic crop coefficient curve where we have a development stage, and then we have a full cover mid-season stage. So this is comforting to see, and the fact that it's fairly consistently at near 1 during the middle of the growing season, which means, again, that all of those fields of sugar beets are reaching near maximum ET, and they are in good agreement with the alfalfa reference. We can shift over to potato fields, in this case about 700, again in the Twin Falls, Idaho area. And during mid-season, again, these potatoes reached about 0.9 to 0.95. And as we talked about, because many potato varieties have a stomatal conductance that's a little bit lower than that of alfalfa, they don't quite attain a KC of 1. But by comparing against the alfalfa reference, we can make an assessment that many of these fields are approaching conversion of energy, maximum conversion of energy into ET. We can go down to Bushland, Texas to answer a few questions. And I'm sorry if my picture here is over the text here, but a few questions we might have is whether or not the standardized Pima-Monteith tends to overshoot or undershoot at high ET or at low ET. Also, how does that equation hold up under very extreme conditions? For example, very high wind speed, which North Texas is very well known for. And then any KC, crop coefficient, that is coupled with the reference ET, does that remain fairly constant under a wide variety of environmental conditions? Here's a picture of the bushland lysimeters growing, looks like a cotton crop, courtesy of Dr. Terry Howell, retired now from Bushland with the ARS. So here, using some data that Dr. Howell provided, we have developed a crop coefficient using the alfalfa reference as a basis from the standardized Pima-Monteith. And then we've plotted those computed KCs versus reference ET itself. So we can see what the KC is behaving like for low reference ET, and then also for some very high reference ET, all the way up to 18 millimeters per day, which is amazingly high and rare to see, but it does happen in North Texas because of the high winds there. We've only plotted for KC above 0.8 because we want to look at just the full cover conditions. And by the way, this is some 1996 data for alfalfa as measured on the bushland lysimeters. We see fairly consistent ratios near 1, which is tells us two things. One, it tells us that the measurement of ET from alfalfa was similar to that estimated by the Pima-Monteith for alfalfa. So that's a good sign. And then the fact that it hovers around 1 for low and high ET tells us that that coefficient, crop coefficient, is fairly consistent over a range of conditions. If we plot the same data versus wind speed, we can see the same thing, that the ET measured by the lysimeter stayed fairly high compared to the equation. That tells us that alfalfa is a pretty robust, determined crop, and it will keep its stomates open even under very hostile conditions. As long as there's water in the soil to support the transpiration, it will provide it. So in this case, we saw ET rates measured as high as 17, 18 millimeters per day, just on a few days. But again, this tells us that the Pima-Monteith does a good job of estimating ET for a wide range of wind conditions, and it tells us that the actual measurement of alfalfa agrees with the Pima-Monteith equation under a wide range of wind speed conditions. Same with humidity. I just won't show those plots. If we move over to a corn crop, we see versus wind speed, we see a similar continuation of a KC, in this case, around averaging about 0.9 for the higher end of the KC. And we see that persist for some fairly high wind speeds. So that tells us that the crop coefficient reference ET method and procedure to estimate ET for a wide range of crops should provide us good, dependable estimates of ET under a fairly wide range of environmental conditions. And as we talked about, I won't dwell on this slide, but again, it's all about energy. And if we use a reference ET like the standardized Pima-Monteith, that is a fairly physically based equation, either with an alfalfa reference or a grass reference basis coupled with the crop coefficient, that should help us under full cover conditions estimate a near maximum upper bound on ET. That should be useful for making comparisons with crop models that have an evapotranspiration component, just to see if that model is staying within energy limited bounds, and whether or not the ET during full cover is approaching those upper bounds as we would expect it to. And then lastly, just quickly, I wanted to say a little bit about nomenclature. The irrigation communities have pretty much been converted to using the term reference ET to when we talk about reference ET, but there's still some usage of the term potential ET when one is referring to reference ET in some of the agronomy communities and crop modeling communities. It's just because of historically potential ET has been used, and there's a continuation of that. But FAO and ASCE and other groups recommend that the term potential be reserved to represent only the ET that is expected from any type of crop surface under well-watered conditions. In other words, when I talk about potential ET, I'm talking about potential ET from any particular crop, such as maize or cotton. Each of those will have its own potential ET, but it's under full agronomic conditions, full water supply. And then if we limit potential ET to that, then everyone knows what we are talking about. Some of the past usages, potential ET has been used in 3 different ways. One, which is no longer recommended, was to describe ET from a saturated surface, like a wet leaf surface, which does tell us the very maximum amount of liquid to vapor conversion that can be established when there's a free water surface, so no surface resistance. The water is right there on a leaf or on the ground or in open water. But for a leaf surface to be wet, we only see that right for a few hours after sprinkle irrigation or a few hours after a rain event. And then after that, we no longer have that. So using that form of potential ET really is not so useful when we're talking about day-to-day evapotranspiration to be expected from any type of surface. Then a second definition that's no longer recommended is to use the term potential when we're talking about ET from some reference surface like alfalfa or clipped grass. For example, what Penman in his 48 paper was estimating ET from a clipped grass, and he referred to it as potential because it was before the advent of the term reference. But now that we have reference ET, that term is recommended when we're talking about that reference surface rather than potential, just so that there's no ambiguity. And then finally, the third usage that we just talked about that is recommended is, just to read it here, is the maximum expected rate of ET from a specific crop under high production agronomic conditions and full water supply. So that's pretty unambiguous, and I think it's the best use of the term potential ET. So this is just kind of a statement, I guess, on what reference ET now represents. It's computed by the standardized Pima-Monteith with a non-zero surface resistance. And it is different from the old definition of potential ET that is coming from a wet free water surface. So in summary, the use of a crop coefficient with reference ET is useful to compare against crop model ET, or actually to use in a crop model as an alternative means of estimating ET. We do encourage the use of the single definition for the standardized evapotranspiration from a reference surface. And it, especially for the alfalfa, it does come quite close to representing a maximum ET. And we should reserve the use of potential ET to represent a full ET from any particular crop. So with that, I'll close. I thank you for your attention, and I'll be happy to respond to any questions via email. Thanks very much.